Here's an introduction to stellar nuclear power to accompany Chapter 16 of the textbook Astronomy from Open Stax. So first, before we talk about nuclear power, let's just quickly cover what is a nucleus. So an atomic nucleus, this is the center of an atom. It's a collection of protons and neutrons. It's doesn't have much mass, 10 to the minus 27 kilograms roughly, or up to 100 times that or so. And it's roughly a femtometer in size, or up to like 10 femtometers or so, but that's the rough order of magnitude. Anyways, at the dimensions that we're dealing with, there are lots of different nuclei, so you can have many different combinations of protons and neutrons. Each one of these we call a nucleus or an isotope. And so there's this thing called the nuclear landscape that's shown here. It's sort of like the periodic table, but for nuclear physics. So in the periodic table, each box corresponds to an element, which tells you how many valence electrons you have, which tells you how many protons you have at the center of the nucleus. Well, here, just the vertical direction is the number of protons. So that's kind of like your periodic table. But then the horizontal direction, this is the number of neutrons. So each box, I can go to a given location, and that'll tell me how many protons I have based on how high up I am, and how many neutrons I have based on the horizontal direction. And these are just the ones that we've measured in the laboratory. There may be more than this. And so just as an example, if I start out on the bottom of this chart and I go up 8 protons, 8 protons corresponds to oxygen, which you can determine from looking at the periodic table. And I go over 8 neutrons, then I get to this region here, and this is this box rather, and this is an isotope we call oxygen-16. So it's oxygen, the symbol O for oxygen, for 8 protons. So that's just our element symbol. And then the number here, the superscript, this is the number of protons plus neutrons, so oxygen-16. Each individual isotope, so for instance oxygen-16, that's one isotope, can have several different configurations. These are known as states, and each one corresponds to a certain amount of nuclear binding energy. So there's a ground state, and then you also can have many excited states of nuclei. So the nuclear binding energy, what is this? Well, it's basically what causes a nucleus to exist in the first place. The main idea is that the mass of a nucleus is less than the mass of the sum of the mass of the nucleons in the nucleus. So if I have that oxygen-16, for example, and I were to weigh 8 protons and weigh 8 neutrons and add that mass together, and then separately weigh oxygen-16, I would actually get less mass when I weigh the oxygen-16 than I would when I weigh the individual parts. So the sum is actually, or the whole is actually a little bit less than the sum of the parts. This is something called the mass defect. So the horizontal axis here is the mass number of a nucleus. The vertical direction is how much less than the sum of the parts is the mass of that nucleus. So you see these are all negative, and this is why nuclei exist at all. So there's a little bit of energy to be gained, to be released into the environment by nucleons combining into a nucleus. And this is just a realization of the mass energy equivalence that you know of as E equals mc squared. If we just take a look at these ground state energies here, this mass defect curve, we can instead think of it as a binding energy per nucleon. So this is the binding energy per the sum of protons and neutrons in a nucleus. We can plot that versus the number of nucleons in a nucleus, and we get this curve here called the binding energy curve. And so for instance, if I take an individual isotope, iron 56, it's very near the peak of this binding energy curve. It's the most bound stable nucleus. If I look at something like carbon 12, it's still rather bound, but quite a bit less than iron 56. And just for comparison, if I take something like the deuteron, this is a proton plus a neutron, then we're hardly bound at all, relatively speaking. So you have these trends in binding energy across our nuclear landscape. And that means that if we convert from one or more isotopes to another one or more isotopes, we can release the excess binding energy into the environment. And so that's how nuclear reactions often occurs, but that it's energetically favorable. And that's where the energy comes from to power stars, is these nuclear reactions. So when we take light nuclei and we combine them into heavy ones, that's something we call fusion. When we take heavy nuclei and they split apart into lighter ones, so fewer numbers of protons and neutrons, that's what we call fission. So just spelling this out in a picture here, fusion is the picture on the left. So we have two nuclei, they combine together, they fuse, and then they can make something else. So they may fuse and stick together, or they may fuse and make two totally different nuclei like you have in this picture. So that's fusion, where you're taking two nuclei together and combining them to make something new. Fission is where you take a single nucleus and then that nucleus splits apart. And basically the reason that happens is there's a different amount of energy for each configuration of this nucleus. Very heavy nuclei are sampling through these configurations. They're kind of like vibrating and wobbling around. And they can find their way into splitting apart into, mostly two parts, but also lots of neutrons will fly off from these fission reactions. So in stars, what we care about for the most part is fusion. So that's really the nuclear powerhouse of a star, is a fusion reaction. So when we think about how does this fusion actually happen, the star is very hot at the core. And because it's hot, that means our nuclei have lots of kinetic energy. They're flying around, colliding with each other. You can think of it like when you're playing pool and you break the rack of balls and they're all bouncing around on the table and colliding into each other. That's basically what you have happening in this star. The nuclei are all buzzing around and occasionally colliding with each other. But it's not enough to collide. They need to actually, fuse. And because the nuclei have protons in the nucleus, there's a Coulomb repulsion. Like charges repel, and so if I try to put two charged particles together, they will repel each other. So we need to have enough energy in between these two nuclei that they can actually fuse. And that hot temperature at the center of a star is what allows the fusion to happen. So what's shown in this plot, the vertical axis is the relative probability of something. The horizontal axis is energy. So if we look at the probability of having a certain amount of energy, our nucleus having a certain amount of kinetic energy in a star, that looks like this line here. So this is something called the Maxwell-Boltzmann distribution. And what this means is you have a high probability of having a relatively low energy, and you have a low probability of having a relatively high energy. We can then look at the probability of a reaction happening in the laboratory, so of two nuclei fusing together. That's the gray curve here. This is something that we call a cross-section. And so you see the cross-section, the likelihood of interacting, is very low at low energies, and it's very high at high energies. And so we have to fold these two things together. You have a high likelihood of having low energy for your nuclei, but a low likelihood of fusing there. You have a high likelihood of fusing for high energy of our nucleus, but a low likelihood of having that much kinetic energy. So when we fold these two things together, we get this red curve here. This is something that's called the Gamow window. And this tells you the probability of a reaction happening in a star. And so here, since we're dealing with relative probability, you're seeing which energies are the most important for the stellar environment. Now, you'll notice then, if I want to figure out what my reaction probability is at the energies of interest, it's a pretty tiny number still, relative to how high it can get. So what that means is that fusion reaction rates in stars are really small. And that's good, because that means stars live a long time, right? If fusion probabilities were very, very high, then stars would burn through all their fuel immediately. They'd be big bombs, and we wouldn't have planetary systems, we wouldn't have the Earth, we wouldn't exist. So these reaction rates, fusion reaction rates in stars are really small, and that allows stars to live a long time. That poses a challenge for nuclear astrophysicists like myself, because then these reactions are really hard to measure because the probabilities are really tiny. And so the probability of making it happen in the lab is quite, it's low, and so it's difficult to actually measure these things. Let's look at fusion in the sun. So in the cores of most stars, hydrogen burning is what is happening. And in the sun, this is mainly processed, these nuclear reactions, through the so-called PP chains. So this stands for proton-proton chains. What you're looking at here are sequences of nuclear reactions where if you followed a given path, that would be a so-called branch of the PP chain. There are different probabilities here in the sun of these happening. The upshot of this is that you take 4 protons and convert it to a helium nucleus. So we can follow one branch and count 1, 2 protons, the 3rd proton, and the 4th proton. So we've consumed 4 protons, and we've ultimately produced a helium nucleus. And so this is what's happening in the sun, is hydrogen is being converted into helium, and there are different pathways here. And so we have, the PP 1, 2, and 3, and 4 chains that can occur in our sun. Now, there's another way to convert hydrogen into helium called the CNO cycle, the carbon, nitrogen, oxygen cycle. The end result is the same. So, you have many different reactions here happening in the sequences indicated by the arrows. The end result is the same, where you consume 4 protons and you wind up making a helium nucleus. So, 1, 2, 3, 4, and our helium nucleus is produced, also called an alpha particle. And so these are basically the 2 ways that you can convert hydrogen into helium in the cores of stars. In the sun, it's mainly the PP chain, and we can see that here in this plot. This is the luminosity in the vertical direction on a log scale versus the temperature. So the PP chains produce not as much luminosity at higher temperatures compared to the CNO cycle, but at lower temperatures, the PP chain produces more energy, more luminosity than the CN cycle. And if we take the temperature at the center of the sun, about 15 million degrees, then we see that the PP chain dominates. And so this is the main way that our sun is converting hydrogen into helium. Amazingly, we actually have direct proof of this. This is not just some theory plus some nuclear physics in the lab. We can actually measure some of the products of these nuclear reactions. And specifically, what we can measure are these things called neutrinos. So if you went back to the previous slide and you looked at those nuclear reaction sequences, you would see that in some cases a neutrino is produced. That's the Greek letter nu. And this is a extremely light neutral particle, and it very weakly interacts with other matter. And so these neutrinos can free stream out of the sun, straight from the center of the sun to us here on Earth, and we can actually measure these neutrinos. So what's plotted here is the neutrino flux in the vertical direction. Horizontal direction is the neutrino energy, and some of these discrete peaks here have been measured. And then very recently, this continuum here, these smooth curves, this continuum of neutrinos was actually measured just last year in this massive detector here. So you're talking about a huge amount of a liquid. That's a person for scale. This thing sits. Ultimately, a neutrino comes in. It winds up producing light in the detector, and you detect it, and you can count them. And so we can actually see these neutrinos from the sun, and so we know this is how the core of the sun and other stars are powered. And that is it for this introduction to stellar nuclear power for Astronomy 1000.